So in this video we're going to use separation of variables to come up with a model for a falling object. So it says an object of mass m falls from rest starting at a point near Earth's surface. Assuming that air resistance is proportional to velocity, determine the motion, or in other words the position of the object. So there's a few things going on here. So the first thing is we need to remember from physics that force equals mass times an object's acceleration. That's the first thing we need to remember. The next thing that we need to remember is that acceleration is the time derivative of velocity. So acceleration equals dv dt. And if we have a position, then we know that velocity is the time derivative of the position. So velocity equals dp dt, where p is the position of the object. If we have a falling object, we could model it using the variable h and say that velocity is dh dt. That would be another possibility. So these are each things that we will need in order to model the position of an object that we draw. The other thing is we want to determine which direction we want to make positive. So in this particular problem, I think it makes sense because we're dropping something from some height, and we probably want the speed to be positive and the position to be positive. We'll make down positive and we'll make up negative. It's our choice, but I'm going to choose to make down the positive direction and up the negative direction. That's something that we need to do. And then we want to look at this and identify that because we're starting at rest, we're being told that the velocity at time 0 is equal to 0. So the other thing that we need to do is think about height. Do we want to know the height from which we drop the object? And so let's say it's 1,000 feet. Do we want to make position at time 0 equal to 1,000 feet or 2,000 feet? Or if we want down to be positive, we might determine that the spot from which we drop the object, that we want that to be, let's say, 0 feet high. And if we decide to make the position from which we release the object 0, then we have an initial value problem. This is an initial value problem because we know the velocity at time 0 and we know the position at time 0. And this is going to allow for us to solve for that constant of integration. The other thing that we need to remember is the acceleration due to gravity. So gravity, if we're working in feet, is going to be 32 feet per second squared. And if down is positive, then this will be positive 32 because gravity would be operating in the downwards direction. So the next thing that we want to recognize is that we're going to be able to find the total forces operating on the object. So if we drop an object from a height, there's going to be, in the context of this particular problem, there's going to be two forces acting on it. So the first force acting on the object is going to be the force caused by the acceleration due to gravity. And so that's going to be given by the mass of the object times gravity. So gravity is an acceleration. Force equals mass times acceleration. So the mass of the object times the acceleration due to gravity is going to be the force operating on the object in the downwards direction. It's going to be the force causing the object to fall. But here is what's different from maybe what we've had to do before. We've always ignored traditionally air resistance, but now we're going to take air resistance into account. And we're going to say that air resistance is proportional to the velocity. Now there's a better model where we let air resistance be proportional to the square of the velocity, and you get to deal with that in the homework assignment. It'll be a harder integral to do, so you'll be pleased to hear that. So we're going to assume that air resistance, which is going to be operating up, air resistance is going to try to keep the object from falling. So if up is negative direction, then minus for air resistance, and then we need a constant of proportionality. Resistance is proportional to velocity. So k times v, where k is a constant of proportionality. And this constant k of proportionality that identified how air resistance works on the object is going to be specific to the physical characteristics of the object. And it's probably going to have to do with mass as a function of surface area. So for example, k will be different for a feather, which has a slower terminal velocity, than for a bowling ball, which has a much higher terminal velocity than a feather does. Think about dropping a feather or a piece of paper versus dropping yourself or a bowling ball. So k is going to be determined by the physical characteristics of the object that's actually falling, and we don't know anything about that in this problem. So k is just going to be sitting there as the constant of proportionality. And then we know that from physics, we know that total force on an object equals the mass of the object times the acceleration. But we know that acceleration is just the time derivative of velocity. So acceleration in mass times acceleration can be replaced with dv dt. So now I can step over here on the left-hand side. So on the right-hand side, I have the sum of the forces operating on the object. I have mass times gravity, and here I have air resistance. But I can replace force with mass times acceleration, or mass times dv dt, which is another way of describing force. So these two things both represent the total force operating on the object. Once I get it in this position, I can then multiply both sides by dt. So that's going to give me an m dv equals mass times gravity minus kv dt. And then when I look at this piece, the variable v is showing up and my dv is over here, and the time variable isn't showing up anywhere. There's no time showing up in there. So I'm going to actually divide both sides by mg minus kv. So I'm going to get, on this side, we'll get m over mg minus kv dv equals just a dt sitting on this side. And now I've separated the variables. Everything with the v in it is on the left with the dv, and everything with the t in it is on the right with the dt. And from here we just integrate both sides, and when we integrate, we know that we get a constant of integration. So my guess on this is going to be a natural log guess. I'm going to guess that the antiderivative is, and I'm going to be naughty with my equal sign and move it over here because I see I'm going to be hard on space. I'm going to guess that the derivative is the natural log of the absolute value of the stuff in the denominator. The variable v is showing up to the first power in the denominator. So I'm going to guess mg, natural log of mg minus kv as my antiderivative. That's going to be my initial guess, and then I'll tweak it to make it correct. And then when I integrate dt, I just get t, and there's my constant of integration. And what we want to remember is that when we have the natural log of crap, and we take the derivative of it, so let's say we take d dt of the natural log of crap, we get 1 over the crap times crap prime, or the derivative of the crap. So when I look at this, if I take the derivative of the natural log function here on the left, I need to get m over mg minus kv back. So using this pattern, I see that when I take the derivative of the natural log, I'm going to get 1 over mg minus kv. I get 1 over crap, but then I would get times the derivative of the crap. So I'd get mg is a constant, mass times gravity is a constant, the derivative of mg is 0. And the derivative of minus kv is just going to be minus k, because minus k is the coefficient on the variable v. So I'd get times minus k. And that's not what I have here. I have an m in the numerator. So I see that to get m over mg minus kv, I would need to tweak this. I would need to multiply by an m over k to get the k to cancel. And I would need this to be a negative. To negative times negative is a positive. So my antiderivative, I'm going to have to tweak it by adding this minus m over k on the front of it, so that it adjusts the derivative of the natural log so that I get this back. If you're uncomfortable taking the antiderivative this way, what we could do is a u substitution, letting u equal the stuff in the denominator, let u equal mg minus kv. and then go from there using the U sub technique. So I'm going to get rid of this because I'm going to need that space over there in a little bit. So I'm in this position right here, so I'm going to multiply both sides by the reciprocal of negative m over k, so that's going to leave me with the natural log of mg minus kv on the left hand side equaling minus k over m times t plus, so I'm multiplying by this reciprocal, by the reciprocal of this, negative k over m, and then I would get negative k over m, which is just a constant, times c, and a constant times a constant is just going to be a constant, so I can replace that with a c. And now I need to solve this for the velocity function. Ultimately, I need the position function. But here I can solve this for velocity, and then we'll need to use the fact that velocity is the derivative of the position function to solve for the position function. And we're going to wind up having to integrate 2 times. So I want to solve for velocity because I need to know position. I want to know the motion or position p of the object, not the speed or velocity of the object. But we're going to solve for v. So we make each side an exponent, base e. So e to the natural log will cancel, and that will leave us with the mg minus kv on the left hand side, and then we'll get e to the minus k over m times t plus c, and then we'll use the technique we used in an earlier video. We want to recognize that we have a base to the sum of 2 things, which can be rewritten as a product of the base to the 2 things, right? Because a base times a base, that means we get to add the exponents, so we would get negative k over mt plus c in the exponent. And then we want to recognize that e to the c is itself just a constant, so we can replace that with a constant. And then the convention is to put the constant out in front in the coefficient position. And now I'm recognizing I have an initial value problem, and I know something about the initial velocity, and now is probably a convenient time to solve for c before I completely solve for the variable v. So if I plug in time equals 0 here and velocity equals 0 right here, we'll get c times e to the negative k over m times 0 will be 0. We'll get e to the 0, but e to the 0 is just 1. So when we plug time equals 0 in, e to the stuff becomes e to the 0, which is 1. It leaves me with the c. And when we plug 0 in for velocity, we get 0 times k is 0. So we just get mg, mass times gravity, is the constant of integration. So I'm going to go and replace that. I'm going to say, hey, mg minus k times v equals c, but c is just mg, e to the minus k over m times time. And now I'll solve it for v. So I'll subtract the mg from both sides, which will take that off. If I multiply both sides by -1, it will change the order here of this subtraction. So I'd get mg minus mg e to the minus k over m times time, being kv, multiplied both sides by -1. Notice that the mg could actually factor out. So if I factor that mg out, I get mg times 1 minus e to the minus k over m times time. My hand's starting to cramp, so the k is getting hard to write. And this is kv here. And then I would just multiply both sides by 1 over k. So I'd get m over k, or mg over k, equaling the velocity. And I could stop here. If it just asked me to find the velocity of the object, I would be done. And we could actually ask some interesting questions here, like we could calculate terminal velocity. We could take the limit of both sides as t goes to infinity, and if we did that, this term here actually goes to 0. So we get in the limit that the velocity becomes mass times gravity over the constant of proportionality. So it turns out that mg over k is actually going to be the terminal velocity of the object, if that's something that interests you. Unfortunately, we weren't asked to find the velocity of the object. We're supposed to determine the motion or position of the object. So we have to keep going. And the idea is velocity is dp dt. So I can replace velocity with dp dt. So I went from having a differential equation right here and then solving that differential equation to now having another differential equation. I have a differential equation again. And I can multiply both sides by the dt in the denominator. And if I do that, if I look at the right-hand side, does the position P show up anywhere over here? It doesn't. And in fact, the only variable, the only non-constant on the left-hand side is the time variable t right here. And so this stuff is a function of t, and it's with the dt. So by multiplying both sides by dt, I just separated variables, which means I'm ready to integrate both sides. This mg over k is just a constant, so mg over k can factor out in front of that integral. Because I'm integrating both sides, I get plus another constant of integration. This is a second constant of integration. So I got one over here that we had to deal with. Now I'm getting a second one over here, but we're not subscripting it with the 2. We're understanding that this one is not the same as this one. And now it's time to integrate both sides. So when we integrate dp, we get p, or position. Position equals mg over k times, when we integrate 1 with respect to time, we just get t. So we get t minus, and we're going to guess that the antiderivative of e to the crap is e to the crap. So e to the minus k over m times time. But recognize if we took the derivative of this, right, if we have e to the crap, and we take d dt of e to the crap, we get e to the crap. But it's times crap prime by the chain rule. So when I take the derivative of this, trying to get this back, what I see is that when I take this minus e to the minus k over m times time, if I take the derivative of this, I'm going to get minus, and I'm going to get minus again, k over m times e to the negative k over m times time, and those will cancel and give me a k over m, positive k over m, which isn't what I have here. So we need to tweak this right here. We'll need to make this a plus k over m, sorry, m over k. I need to multiply by the reciprocal of the thing that I'll get when I take the derivative. So multiply by m over k plus that constant of integration. And then your check on work is to take the derivative of that and make sure you get back the original statement. So the derivative of t is 1. The derivative of m over k times e to the negative k over m. The negative k over m comes down and gives us a negative 1 in front of the e, and we get e to the crap. So now I have the general solution of this differential equation right here, but because it's an initial value problem and I'm assuming position at time 0 is at 0 feet, we plug that information in and solve for the constant of integration. In other words, we're finding the particular solution, not the general solution. So position is 0 when mg over k times time, we're replacing t with 0, so this will be a 0, so we'll get m0 plus m over k times what? Times e to the 0 times this stuff is e to the 0. E to the 0 is 1 plus the constant of integration. So solving this for c, we're really going to get the opposite of m squared g over k squared as our constant of integration right there. So we would then, using those initial conditions, replace the c. So we get mg over k times t plus m over k e to the minus k over m times time plus, it was really minus, it was minus m squared g over k squared. And then what I'm not going to do, because I'm really out of space, is I'm going to recognize that I have mg over k showing up in both terms. I probably would want to factor an mg over k off and clean this up a little, just a little bit more. But this is the position function. So in the homework, what you're going to do is do the same problem, but you're going to be assuming that air resistance is proportional to the square of the velocity. That will be the tweak in the homework assignment.